So here's that idea again applied with satellite imagery and air photos. In these days, air photos are quite often taken digitally. On the left, we have comparatively coarser information at the 30-meter resolution, so 30 meters on the side of each pixel, compared to, on the right, finer resolution of an air photo, a digital air photo, with 1 meter spatial resolution on the side of each pixel. And then overlaid on top of that, you have a vector representation of the coastline and some of the features that are on it. So here, hopefully, this is just showing that difference between what cell size does in terms of being able to accurately describe what's on the Earth's surface and that whole phenomenon of aggregating information within a pixel. So the larger, coarser cell sizes are doing a worse job of describing the Earth's surface. The finer, higher resolution data does a much better job of describing what's out there. And there are benefits and trade-offs to and drawbacks to either of these things. One of them is that the 30-meter resolution data set will be faster computationally. It will occupy less space on your hard drive. The finer resolution data will take a lot longer to process and will take exponentially more data storage space on your hard drive. So to get an idea about that, looking here again at kind of a general study area, vector data, very good, very precise, very distinct, clean boundaries, and very good descriptions, therefore, of the area and length relationships. Imagine this is a land cover type map. With a raster of the same area done at the 200-meter resolution, we see it's very blocky, very clunky. It's doing a job of describing all those features, but not terribly well. If we were to sample that information and record it at the 50-meter resolution, a much higher, finer resolution, then we're doing a much better job of describing the area, not as good as vector, but doing a better job of describing the area relationships of each of these land cover types. But the data set's going to be 16 times larger. So, you can imagine what's going to happen as you get higher and higher resolution data, which we're able to do these days with our modern technology. We're going to need more and more storage, larger hard drives, faster processors, more RAM. We're going to need very good, powerful workstation computers or server farms to analyze the data, maybe even to display the data, depending on what the resolution is. So cell size is a critical thing to get a handle on in your data sets, to predict how much space you're going to need to do your analysis. You'll quickly discover when you do a lot of raster analysis that flash drives probably aren't going to cut it. You're going to need to start looking at solid state drives or hard drives or cloud-based storage on the internet in order to handle the massive data sets that you can generate quite easily by using raster data. So to drive this idea about storage home, here's a sample of 3 different grid cell sizes for the same study area. At the 100-meter resolution, we're looking at 4 cells encompassing that area, describing that area. At the 50-meter resolution, it's 16 cells that describe that area, so we're getting more detail. At the 25-meter resolution, even more detail, requiring 64 cells. So if we think about the cost in terms of storage for rasters, if we, as the slide is indicating, if we reduce the cell size by a factor of X, then we're going to require 2 to the X more storage and computation capabilities to handle that information. So very rapidly, when we get higher resolution data, which everyone wants, more detail about a study area, it's going to consume more and more storage space on our computer systems. And these days, with hard drive capacities where they are, and processor speeds and RAM where they are, this seems like it wouldn't be a problem. But when you start looking at very high resolution data that we're getting now from drones and digital aerial photography, we do still clog up and tie up and have our computers just kind of sit there for a long time doing computations when we ask them to do very intensive calculations using very high resolution data. So the resolution of your cells are going to be based upon your underlying coordinate system, whether it's geographic or projected. And the point on this particular slide is to emphasize the idea, the concept that we are very interested in distance and area relationships whenever we're doing geographic analysis. So we need those properties in order to be able to do proper calculations. So it's best to use rasters that are projected, not unprojected. So true geographic coordinates, remember those are based upon the spherical Earth. Those really aren't sufficient for analytical purposes. So if you get a raster in geographic coordinates, you should, under best practices, reproject that information to match whatever coordinate system is being used for your particular project, whatever coordinate system, a projected coordinate system, is most appropriate for your project. Okay, so geographic, true geographic coordinates in degrees, minutes, and seconds, not so great for analysis. Projected information, which then typically is going to be presented either in meters or feet as the unit of measurement, much, much better and preferential for doing spatial analysis using raster data model data sets. So let's compare these two major forms of numerical data that you're going to be seeing in your raster data sets. And just as a general rule, we measure information in bytes, kilobytes, thousands of bytes, megabytes, millions of bytes, gigabytes, things like that. The more or the larger that number is in terms of bytes, the more space it's going to consume on your hard drive. Okay, so for integer values, with an 11-bit pixel, 1 byte of information storing values from 0 to 255, a 16-bit pixel stores values from 0 to 65, 565, 24-bit pixels stores 0 to 16.7 million in terms of that's how large the number is. Okay. Floating point values, so we add to the integer the decimal place and then decimal values beyond the decimal place. That requires the use of a 32-bit pixel or 4 bytes of information. So right away, we need 4 times as much space to store values from 0 to 10 if we add a decimal place to them. Okay, so comparing the lowest category of integer values to floating point values is a very substantial difference, and it doesn't really matter if they're just zeros or not. When you create floating point data, it's going to massively increase the size of the data set because the system will add that decimal place and zeros after it. So the long story shortened is integer values will consume less space on your hard drive, and they're very good for categorical nominal levels of information, perhaps discrete values if you're using raster data for kind of discrete objects on the Earth's surface. Integer is going to consume less space than floating point values. Floating point values are much better for describing certain types of surfaces and measurements that we might make at the Earth's surface. So precipitation values, for example, usually aren't nice round integer values. There's typically fractions of values, decimal places that are required for that. Average annual temperature can be measured and presented in straight degrees, but it can also be a fraction of a degree. So floating point value is good for that. Elevation is usually not stopping at the 1 meter increments and steps across the landscape. There are fractions of a foot, fractions of an inch that can be contained in pixel values. So environmental data, if you think about how this all plays together, using surfaces describing entire regions with high resolution data at the floating point style or type format is going to consume a lot more space than integer values that are trying to depict the same thing across space. So something to keep in mind here about the differences between rasters and vector data is that data set can have different meanings. When you're looking at a raster data set in particular, it can mean something else. So a raster can be a single grid array of cells describing some environmental phenomenon or some human phenomenon across space as a surface. A variation of that is known as a multiband raster, where there are multiple grids of the same cell size at the same resolution containing different forms of information but all lining up together. So satellite imagery or aerial photography done digitally are examples of this, where each of the individual bands or layers of information contains some other piece of information about that Earth's surface that's related to everything else in that raster. So again, using a satellite image as an example, at minimum, you're probably going to have at least 3 bands in that image that are the red, green, and blue values of whatever the landscape was combined together to form the colors that you see if you're out in space or up in an airplane looking down at the surface. Quite often, satellite imagery is also going to include other bands of information, typically in the infrared range, so measuring infrared radiation coming up off the Earth's surface. The red, green, and blue bands in a satellite image are recording the amount of radiation in the red, green, and blue portions of the EM spectrum. Okay, so each band is a different set of information. Each pixel has a value in each band. And so data set with raster, okay, can mean that. It can mean multiple grids within the same data set describing the same area in different ways. That's very different from vector data, which usually you've just got a polygon. Okay, and that polygon is itself one thing. There's only one, but we can put multiple attributes attached to each polygon. And so that's what the tables do. Okay, so we've got one set of geometry, multiple attributes that can be attached to it with vector data. With raster, each of those attributes has to have its own raster, but they can within these multi-band raster structures. Rasters are information stored in single bands or multi-bands, describing information about the surface of the Earth. In ArcGIS, rasters are stored 3 different major ways. As individual raster data sets within the filing system as not features, but as components of a geodatabase. So you can store rasters within a geodatabase. You can actually store rasters in the same geodatabase that you're storing vector information. My preference is to actually create separate geodatabases, one for vector data, one for raster data. But geodatabases allow you to mix and match and put those things together if you so choose. And the other way that they can be stored is as standalone rasters that are managed from within a geodatabase. So you can run the operations on the data set within the geodatabase. You say basically within a GUI for a tool, you'll select that raster data set within the geodatabase, and it looks like it's operating on the data within the geodatabase right there, but actually it's stored somewhere else, and it's doing the operation on that. It transfers the operation to where that standalone file is located. There are some advantages to that. There's one type of data in particular that's really, or a data set that's really handy to manage that way. Most of the time, you will probably be dealing with rasters as either individual data sets that you will manage that way, or you'll store them in geodatabases because it's a handy container to use for transferring your data to other people. The great example of using a geodatabase to manage individual standalone rasters is the Mosaic data set. So a Mosaic is a raster data set that's comprised of data that does not need to be adjacent. So it does not need to be a continuous surface. Okay, so this may be a little bit difficult to visualize, but imagine you have 3 different study areas in 3 different national forest units in Washington, Oregon, and Idaho. And you're interested in doing the same type of analysis on each one. You have the same information about each of those particular units. You can combine them together in a Mosaic data set, all raster-based information, and then you can run operations on all 3 of those units at the same time as if they were one individual raster, and that's what the Mosaic is. So the Mosaic essentially lets you take that information and treat it as if it was a single raster. Okay, mosaics within ArcGIS are pretty powerful. They can have different projections, different resolutions, different numbers of bands if they're multi-band. They're pretty flexible things. They're pretty cool. Anyway, but what it is, it's that third example of how rasters get stored. It's individual data sets stored somewhere else. You mosaic them together within the geodatabase, which is essentially saying, all right, now we're going to treat all these things as the same data set. They don't have to be contiguous. They don't have to be adjacent to each other. They can be, but the power of this, the great power of this particular approach of creating a mosaic is that they don't have to be adjacent to each other at all. And so if you use these, it allows you to do the same types of analysis very rapidly on discontinuous areas located in different locations, but within the jurisdictional boundaries of whatever agency, corporation, or whatever it is you're working for. Another example might be if you're working for a resource extraction company, like a forestry company that has units located on different parcels, even on the same mountain. You could use this information approach to manage your data and do analysis and save a lot of time by just mosaicing them together at the beginning and then conducting everything that you need on them. And you get a simple, relatively simple output then all at once for all those units simultaneously. So anyway, mosaics are really interesting, an interesting approach and solution to the problem of if you have the same data types that are not adjacent to each other. This gets around the limitations that otherwise might apply to individual rasters for individual pieces, parcels of property, or study areas. Earlier, we mentioned that you can generate rasters from vector data. You can actually go the other way around. If you have a raster and for some reason you need to create vector information from it, you can. You just use the special tools that are built into your GIS. You feed it the input DEM, and you give it instructions as to how it's going to create the vector information. Raster to vector conversion, as the title of the slide indicates. So we have a raster. It could be describing a road or a stream. It doesn't really matter what it is. It's some linear feature on the Earth. And you can calculate or you can extract from the raster the cell centers. And so then those become point locations in space. And those point locations can then be linked together with lines to create a line data set. And there we go. You can also create, if you think about it, you can also create polygons from this. Again, it just depends on how the tool is written. You can go raster to vector with the understanding that the vector data that you create is going to be less accurate, precise, and truthful than a vector data set that was created initially as a vector data set using vector techniques. However, if you do need to convert your raster information back to vector for some reason, you can. You just find the right tool set in your GIS system, and you'll tell it, there'll be certain parameters of the tool. For example, on top here, it says we're going to use any cell that we can, and at any location in the cell, doesn't really matter, to generate the line, or we're going to pick the location that's nearest the center of the cell in order to get our line parameters. And so it uses slightly different pixel locations, perhaps, for selecting where those points are, depending on which rule you choose. And that's something that will vary depending on which GIS system you use, whether it's ARC or something else, when you use this kind of a process.